Good evening, everyone. On behalf of IEEE CEDA Bangalore chapter, it gives me an immense pleasure to welcome you all to the IEEE CEDA Industry Insight Series Episode 3. This series is designed to bring together industry leaders and professionals who share the real-world insights, experiences, and emerging trends in the semiconductor and electronic design domains. We are truly delighted to see such an enthusiastic participants from students, researchers, and a lot of professionals joining us today and from the the last two sessions. Thank you all for taking the time to be a part of this session. So without any further delay, it's my pleasure to introduce our esteemed speaker for today, Ms. Sweta. Sweta is a senior engineering leader in the semiconductor industry, currently serving as a senior manager at SanDisk. With close to 2 decades of experience, she has been driving high-precision semiconductor design solutions while leading and mentoring high-performance engineering teams. She has held key leadership roles at Western Digital and has contributed significantly to the complex design programs, combining strong technical expertise with people leadership. Her career journey also includes experience at Tata Elxsi Sankalp Semiconductors to building a solid foundation in semiconductor designs. Beyond her professional work, she is an active advocate for women in technology and is involved in leadership development and community initiatives. She is also a storyteller and a Toastmaster, bringing a unique blend of creativity and communication to our work. We are truly excited to have her with us today and look forward to an insightful session. Now, without any further delay, I would like to invite Sajal sir to address the gathering and we'll kickstart the meeting.
Hello everyone, good evening. I can see 37 participants. I think it's good forum, and I would like to thank Shweta. Shweta was my old colleague. We are working together on multiple projects. When I was thinking about the speaker for this series, like this is a continuous series, you all guys know, whoever joined last two series, it's a monthly series in which we are bringing industry experts to talk about this, and this month's topic is layout. So when I was thinking about this, I directly, Shweta came to my mind and she said yes. So that is very good part. So thank you, Shweta. And I hope people will learn today. And sometimes we always think layout is the easy part of the design, but as our semiconductor is progressing into difficult nodes, I know I cannot imagine. I know like layout is very difficult and it's very important. If you mess up with the layout, your whole design go for the toss. So thank you, Shweta, for agreeing for this lecture and looking forward to it. So without further delay, over to you, Shweta.
Thank you so much, Sajal, and thanks, Vamsi, for the wonderful introduction. You have done a lot of research through my LinkedIn profile. Looks like you found all the data from there. And as you mentioned, I will make sure that today's session don't become a boring technical lecture. As Vamsi said, I am a storyteller. I will try to build that in a story format so that just like these stories which you have heard from your nannies and daddies, you'll not forget this story also today. So with that, let me share my screen. Okay, fine. Okay, I hope my screen is visible to you all. And as I go in the presentation mode, I'll not be able to see you all. So I'll just hope that I'm audible. If anytime you are not able to hear me, you're not able to see the content, please stop me and we can continue. Okay. So before I start, just to get an idea, most of the people joining today are from different colleges. Are you all students? Maybe a thumbs up or raise of hand if that can be done. Okay. And I assume that most of you are student, but at least from the VLSI or electronics background, so you understand the basics. Okay, great. With that, let's get started. As a few minutes back, Sajal was talking about that how with the technique, the transition of different nodes, layout is becoming so important. So in today's discussion or in today's session, we will see something which sits at the heart of semiconductor design. And it looks very easy, but if it goes bad, it can break everything. And that is layout design. So as you see here, right, layout design decides everything. Someone has designed a wonderfully, perfectly working circuit, but it went to silicon and it did not perform. We once had one incident.
Sorry to interrupt your story. Maybe you can hide that lower bar. If you see stop sharing, right to half, correct.
On, right? Is it now better?
Yeah, that's perfect.
Okay.
Yes.
Okay. So, yeah, going back to the story I was sharing, it once happened that we had to go for a revision tape out. There was something to be fixed in the silicon, which was working perfectly with little bugs initially. So some changes were to be done. Now that it came to the layout designer's hand, they found, oh, if I'm improving this, let me improve something else also. Some few changes were made, and then that silicon did not work. No change happened in the circuit, in the schematic, but the layout did not work. That is what the impact of layout design is in the working of a chip. So it's the layout design which actually defines how or what the yield will be in the silicon. As we have to understand the whole thing, it's better to go through the complete flow. You all must have studied this already in your colleges, I'm sure, how the overall flow of VLSI design is, right? It always starts with the specification. Any chip you have to make, you have to have the specification. Based on that, you will create your schematic, you'll make symbols, make the next level schematic, you will simulate it, perfect schematic is ready, and then you will give it to the layout design, right? Which is where my team or where I work, that comes from. We will take your data and start making a layout. What we are doing here is we are doing a translation, and in the coming slides, I'll also talk in detail about it. And while making the layout, we also will take care of few things like whatever we are drawing, it should be fabricatable. So design rule checks, etc. will happen. Extractions will be done to check that what I'm drawing is meeting the requirements of the circuit. And if everything goes fine, then we go for tape out. If things are not that good, then we go through the whole cycle again, right? So in the overall flow, this is where the layout design sits. Now, let's take a step back. We have schematic. You all must have seen schematic. You all must have seen circuits in your textbook, in your labs. And then maybe you must have seen chips, right? Or at least any device what you use today, it has chips inside that, right? So this schematic has to get transformed into a chip, which means it will go on silicon, right? Can this schematic as it is go to the silicon? No. A translation will be needed there, which is where layout comes into picture. Now, as I use the word translation, right? These days, all of us have wonderful smartphones, right? And all our smartphones have this lens, Google Lens or some lens with which you can do the translation. I remember we were in Hong Kong and I was thirsty, I wanted to drink something, but a lot of things which were written on the bottles, I was not able to understand. Opened the lens, tried to do the translation. It was fresh juice, but what the translation showed me was a live liquid. Technically, what it showed was correct, but it was something which was very concerning, a live liquid. So why I'm sharing that story here? What a layout designer, the way he or she will translate the circuit into, can be technically correct, but can still fail to become the kind of chip they want or to deliver the performance which is expected if the translation is not done in the right way. Hence, for a layout designer, it's very, very important that you understand the fabrication also. In this slide, we can see a cross section of inverter. I'm sure you all must have seen it in your textbooks or in different videos or lectures, etc. I've just put it in a tilted form so you can see it this way. We have the PMOS, we have the NMOS. Of course, what we will start with, we'll have to have N-well, we'll have to have the source and drains for the PMOS to get formed. Similarly, on the NMOS side, there'll be a gate. Now, if we see that side by side with this side on the left side, this is the layout. What we are doing the exact same thing, which will go in the fabrication, right? See, we are drawing the N-well, we are putting the device there, which is the active or AA, different names used at different places. And then there'll be, of course, a channel, a gate, which is what will make it actually a CMOS. And then the connection of same and the metallization and so on and so forth. So layout design is nothing but pure translation of circuit in fabricatable masks. This is what will go for fabrication, and this is what will decide that whatever the intent of that circuit designer's circuit design was is actually going in the correct way for the fabrication. I hope we are clear so far. Now let's go deep down and understand that what are different type of layouts. There can be many sub branches inside, but I'm trying to go for the main 3 branches, which are standard cell, analog, and memory layout. We'll spend some time here to understand the basics of layout. Standard cell layouts. You must have heard this term before, and if not, it is actually the foundation of digital design, and sometimes for any mixed signal design. Whenever you have to make a house, a lot of you must have seen houses around, be it a multi-story building or be it a small independent house, there is one thing common, which is the basic building block, the bricks. There can be variety of bricks. It can be red brick, it can be the cement brick, it can be stone brick. And depending on the requirement, like you want the house to be stay cool, you will go for red brick. You want very much strength, you will go for maybe the stone bricks, and so on and so forth. But the brick is always the basic building block. Same way for the VLSI design, the standard cells are the basic building block, be it for our schematic, be it for our layout. Now, talking from layout perspective, as it is the basic foundation block, it's very important that it is laid out correctly. So, as the name also suggests, standard cell, there are few things which are always fixed for a standard cell. As we are seeing here, there will be always a pattern, like there will be rails and our MOSes will be sitting between it. There will be a fixed height for different technology node. And how the height gets decided? It gets decided based on how many routing tracks probably we want, how many hit points. If you talk from the PNR perspective, how many hit points we need. Based on that, the height gets decided. The height also gets decided based on the biggest PMOS or NMOS we need in that particular library, depending on where you are going to use it, right? So these things will decide my height, but the width can vary depending on how many devices are there for that particular standard cell. An inverter will be smaller, a buffer or a latch will be bigger in size. PMOS on top, NMOS at bottom, VDD buses on top, VSS at bottom, and in between the connection for them to happen. So this will be the basic structure. As you will design different cell, there will be some more changes coming there. Here I'm just showing you one reference picture. if there is a chip, say it is a very digitally dense chip, it will be filled with thousands or millions of standard cells. And these standard cells, as you see some lines here, right? These are our rails, and we will always be putting it on them. That is the reason we are saying these are the standard block. They always have to be in a particular form so that we can abut them, we can keep them together, and we can utilize more standard cell in a given smaller area. And yeah, just to give a background, when many standard cells are put together and a logic is created with multiple gates, we call it macros. Let's see one actual layout of a standard cells. I will not go and explain the nitty-gritties or the very basics of this layout design, but as you can see here, and we were talking before also, standard cell will have very fixed rules or guidelines to be followed, and more you follow them, better your library will be. As we know, this is the basic building block. Our chips, performance, power, area, all that is dependent on it. So never think that it is very easy, it is the smallest thing. The more you are able to innovate here, will get replicated that many times at the next level, right? So there'll be some requirements very specific here, like half DRC rules, so that and having the power nodes at the edge so that you can do abutment, etc. You should always have substrate connections so that you don't have to add them on the top level. Don't do all the routing in poly, which is the gate. If we take care of all these things, we will always have a library which is good for power, performance, and area. And that will define the future of your chip. Okay. Next comes the analog layout. Analog layout, unlike the standard cell, is something very relaxed. Like, just imagine you were on a trip where all the things were defined exactly, that every day you have to do 1, 2, 3, 4, 5 things. Suddenly you come on another trip where everything is left on you. You can decide how things can go. Your end goal is something that, fine, in this particular trip, maybe you are supposed to explore the culture of that country, but you will make all the decisions. So that is the reason analog layout is also called as a layout art. Because here we don't have very stringent guidelines given, but the end goal needs to be met. For example, some of the analog circuits, if I can talk about, some names you guys also must be aware of, say regulators, PLLs, VCOs. You'll see they all will have different requirement, right? So it's not something like one shape fits all kind of thing. Here, every time looking at that particular circuit, you will have to create the layout differently, but the basics remain same, which will be the floor planning and placement. As we are talking about analog circuit, right? There will be requirements where devices need to behave in the same way. There will be requirements where different signals, which are very critical. For example, there is a reference signal. The reference cannot go bad. Otherwise, the whole circuit will perform in a different way, not like you have planned. So floor planning, the placement of devices, not just at the module level, like at your basic circuit level, at the top level, at the chip level, is also very important. So when we are working in analog layouts, we have to have all the concepts with us and then look at the circuit and take decisions on the go. I'm just showing few things here. I hope you might be aware of it as well. Things like device matching, as we are seeing interdigitization, common centroid. Why exactly do we do it? If anyone wants to speak, if that is allowed.
Yeah, everything is allowed, don't worry.
So if you have ever heard about matching of devices, do you know why do we talk about matching of devices? Okay, for the interest of time, I'll only speak now. Say if this is my silicon, right? There are many chips here. There is something called gradient effect. You all must have heard that. So the way things will be seen at this edge to the way things will be seen at this edge will not be similar. If any of you have stayed in colonies where there were houses in a row, you might remember that people always used to, some people will always look for that corner house because it will have extra area at the sides, and some people will never like those corner house. They want to be tucked inside because the corners house are more prone to theft and all those issues, right? So same way here, the things at the corner can have more effect of stress. So our important devices need to be in center. That is why we try to do the digitization in such a way that we are, when if say there is a problem with the etching process, right? Problem in the sense it is happening differently. The way it started here to the way it started here, there is a gradient change. The effect which will be seen by say device A is also seen by device B in the same way. That is why we interdigitize it and not just keep them all 6 fingers together, Else, most of the effect will be seen by, say, device A compared to what device B is seeing. The same way we have another concept also of common centroid. So in interdigitization, we were just placing them as multipliers, and here we are putting as fingers. I hope multiplier finger concept we understand, or I'll just quickly dive into that as well. So sometimes when we design a circuit, the designer has done the circuit design saying this transistor has to be 6 micron width and has left it on you. You go draw it. In the standard cell, I have a fixed height. If I'm not able to fit it as 6 micron, I will break it and make it 3 micron 2 multipliers. Multipliers means same as maths into 2. So total width still came same, 6. So it might be okay. But as soon as we come in into the world of analog, it might not be okay in some cases, because as soon as we broke a transistor, right, now as one finger or one multiplier, it has only one capacitance on the source side, one on the ground drain side. But as soon as we break it and say we have placed them like this, like different multiplier, we have broken the device in such a way that there are, in place of one capacitor of source or drain, there are multiple of them, as many as multipliers are. But as soon as we went in common centroid and we started sharing them, say if the number is odd, and so the number of drain connections and the number of source connections are different, then your capacitance of source and drain also changes. And in many cases in analog layout, that will not be accepted. If say the device performance is very critical and even that parasitic can affect the circuit, so it will not be allowed. So that is why when we are drawing analog layout, as I was telling before, it is like an art. Means you have all the data, but everyone can draw it differently. Hence, it's very important that you understand why you are drawing it, what is the main intent, and you take right decisions. Okay. So this was about the device, and similarly, there are routing constraints as well. Let's see if I discount this. Yes. All right. Yeah. So there'll be routing constraints as well, right? As it's analog, it will not always be the minimum voltage or current requirement. So depending on the requirements, you'll have to understand the circuit and accordingly make a decisions of the width and the wiring length. The concept of shielding also I'm touching upon here. In case if you know very good. If you don't know, shield, right? As you must have heard, the word shield means you are protecting something against anything outside. So shielding means if the routing is very, very critical, we don't want anything to affect it, we cover it with, from all four sides or sometimes two sides, with another stable power or ground line with the help of another metal. Right? So these kind of constraints will be there, which you must understand if you are doing analog layouts. And with these constraints in mind, you can take decisions. So analog layout is something unlike our standard cell counterpart, where even designers will be very much interested in layout. I'm not saying that other places they will not be, but in the analog layout world, you have to understand the design just like a designer. Then only you will be able to take good decisions. And it's also very important that you keep connecting with, keep communicating with the designer to understand what that circuit is supposed to deliver, so that you are taking right decisions and making a good analog layout. Okay, with that, I'll move to the next part. But before that, yeah, let me touch base upon a few more very interesting things which you will only see with analog layouts. As we were talking before, right, the corner effect, right? So when we have very critical devices, we don't want them to see very huge different effects or issues because of the gradient effect. So we keep some dummies. Means there'll be transistors which are placed there, mostly connected to ground or power, but they are there so that the effect of etching or that effect of when there is in the fabrication process, you must have seen that the when the doping is happening, right, it will not happen straight, it will happen at an angle. So there can be different effect at different location. So at least the main devices are seeing almost similar kind of effect, and the corner stress, etc., is seen by only the dummy transistors. We will also have guard rings around it. Like guard rings, what it does, it is more contact on the substrate. So we save ourselves from the noise. We also make sure that our resistivity on the substrate side is lesser. We are lesser prone to latch up, etc. Okay, and then metal density fill. So as we were talking about shielding before, there are very critical routing. We don't want anything else to go on top of it. We will use the metal pattern on top of these routings so that no other effect of different signals come on it. We will talk more on it in case if you are not understanding that how one metal can affect another metal. We will talk on that in coming slides. Also, every new layer is a stress, right, on the layer within it. So if we don't want the stress to be come in, any random way, so we do specific density fills so that the stress is seen evenly. Pattern fill is also on the same line. And in IPs, when we say IP, it's like there are multiple subparts of a bigger chip. What we do there is the analog part, the sensitive part. We try to always have them at one corner so that the noisy part, the digital part is not affecting, the switching part is not affecting our stable parts much. We'll also put guard rings around it, make sure the stable substrate is there. And sometimes if we are in, say, triple well processes, etc., we even create a separate well for it so that these noises are, the digital noises are not affecting our analog IP. So analog layout is a very wonderful world on its own. And there is a lot to be covered there. Probably we can have one session on analog layouts itself. But for basic understanding or for the first kind of know-how, I think what we are hearing today is good. Make note of the words if something is not very clear, and I will be happy to help you with those at end. With that, let's touch upon the memory layout. As we are in the era of AI. Everyone is talking about memory. You all must have heard it around. Memory layouts are something little different than our previous two things which we talked about, standard cells and analog layout. Memory layouts are something where area and performance and speed, all of them matter a lot. You cannot just go with performance like we were just doing in the analog. Other things are also important, but performance is very important. So if you are a little big in area, you can go relaxed. Here, you have to give that performance in the compact area. For our discussion purpose, I'm using SRAM here, but there are a variety of different kind of memories. We'll talk about them as well. So any memory will always have a core structure, the basic building block of that memory. For SRAMs, it can be our 6 transistor cell. For DRAMs, we will have 1 transistor and capacitor, and so on and so forth. So that is our smallest unit. How we design the layout of that will define how compact, how good, how dense memory you are able to create. So that is why memory layout also is a wonderful place to get expertise in. There are people who are known for doing best memory layout. A lot of time there'll be selective few who will be doing these bit cells, because these bit cells are like the main soul of the memory chip, you can say. So they always have to be smallest, and they always have to be done such a way so that we can organize them very well. I hope SRAM is something we all understand. We must have studied it in our first or second year. So if you remember, there will be some bit lines and there will be some word lines which are nothing but row and column decoders. And based on all that, we have to decide the size of the cell. So in memory layout, that becomes our constraint, right? So with those constraints, and while being the smallest and fastest unit, we try to create the memory layout. It is very repetitive, and hence it's very important that we save on the area as much as we can, because even 1 micron, if you save, it gets repeated 1,000 times. In totality, you save 1,000 micron, right? So, and it's a pitch-based layout. Pitch-based means there'll be a fixed template, as we were talking about row and column, and within that same sizing, you have to maneuver. Just showing few categories here, just to give an idea. See, all of them are 6 transistor layouts only, but every time it is done differently. And depending on where it is getting used, say at corner, say at center, different type we will be using. So even though it is repetitive structure, it is not monotonous. You can innovate, you can use your creativity and can make it differently each time. And as we were talking, here, for example, we are showing SRAMs, but we have variety of memories. There are SRAMs, DRAMs, flash memory, CAMs, and register file. All of them have different requirement and hence different guidelines or different things to fulfill. And based on that, the layout for each will change. We are not going today in depth for each of these specific memory types, but I'm sharing it here for your reference. You can go back and look at them to understand how it all changes. A quick note for you will be, look for their basic building block, which is their bit cell. The way the bit cell will be, that is what will define how the overall memory design of that particular memory type will be. Okay. I'll move forward. I think we'll finish things and later we will go for questions. So far we did see the 3 main flavors of the layout design: standard cells, analog layouts, and the memory layout. But there are some challenges which are there in all of them. There are many challenges, but we can broadly put them into these 4 categories. Parasitics, as the name itself says, parasitic, something which is unwanted, but it came. signal integrity, congestion, and the verification constraint. Let's dive into each one and understand them more. So when we were talking about drawing layout, right, translating the circuit into something fabricatable, devices are put. Now devices need connection. It will be done through different wires. Anything which looks like a wire to you, you'll see, okay, this is the driver, this is the output, there is a wire in between. Every wire is nothing but a combination of resistor and capacitor. So every time you are drawing a line, you are drawing unknowingly many resistors and many capacitors. So these hidden resistors and capacitors are the parasitics we are talking about. What do they do? These unwanted capacitors and resistors will delay your signal, because there is R, so it can create some drop. There is C, it can reduce your speed, your swings will change. Power in the same way. Longer routing is there. Longer routing means a bigger R, so there will be a big drop there. What you were expecting is not reaching at the location. And signal distortion will also happen. Long back in the era when the gate lengths were wider, the gates used to be something where people used to worry that, oh, this is something which can impact on my circuit timing. This is what can make it delayed. Now with the smaller technology nodes, our gates are smaller, they are switching faster. But as more and more gates are coming, complex designs are getting made, our wire lengths are becoming longer, and this RC, this delay is something which is killing us more. So in the advanced nodes, parasitic or RC delay is something a layout designer has to be aware of and take care of, starting from the placement time itself. As we are seeing here in the second figure. Let me go. Okay, laser. So as we can see here, right, the expected signal has to be like this, but as it is a long routing, distortions will come. What will you do? You will now have to amplify it at given intervals, or in the beginning only. If you are aware, you are not just going and drawing something, you are drawing the layout with proper awareness. You will try to have this driver and the destination close by so that the distortions are less, or you will go for higher metals where the resistivity of the metal is better, so that you can take care of these distortions on the way. Right, so that's why it's very important that we understand these challenges. And parasitic RC is one of them, which we just covered. Now, signal integrity, right? What is signal integrity? Am I going in like a monologue mode? Somebody wants to talk? Or you are enjoying to hear me? Should I continue?
Actually, we also got a few questions. I hope participants are following.
Okay. Okay, I can look at the question. Actually, we have few slides left. Let's finish it and then we'll
Sure.
dig into
And we are
questions.
getting a huge thumbs up from all the participants.
Okay, thank you so much. So back to signal integrity, right? The word integrity. What is integrity? What we show, that is what we are. Sorry, somebody wanted to contribute?
No, please carry on. It's just
Okay, so integrity is, we say the integrity of the character. What you show, that is what you are. So what I'm transmitting, I expect my receiver to receive the same thing. If that happens, then the signal integrity is good. If that is not happening, that means the signal integrity is bad. Something on the way is changing the character of my signal. And what it is, again, those parasitics we were talking about, the R's and C's, the inductance, all those things which we have not planned, but it came. So we need to be aware of them and take care of them in our drawings. Now, as you can, a lot of things are written here, so you can see it. But to give you a general idea, signal integrity, how it will, the distortion, how it will impact. The false switching can happen, right? Because there are glitches now in your signals. Timing failures will happen. There'll be, just a second. I'm sorry, give me a minute, please. Is my whole screen?
Your screen is visible and it's in signal integrity.
I'm struggling with it. Just a second. Okay. I just felt that it is frozen. So, okay, I hope it's visible still. Yeah, so as we were talking about signal integrity.
No screen is getting shared.
Sorry?
Screen is not visible.
Oh, okay. How about now?
It's coming, just a second. Yeah, now it's visible.
Oh, yeah, sorry about that. I saw some pop-ups. So, yes, talking of signal integrity, as we were talking about that, it will have some effect in the performance of my chip. And that is why it's very important that we understand it and we also know how to take care of it. As we understood, it's a distortion, how to remove it. The unwanted R's, the unwanted C's should be less. So again, pick the metal and the width according to your requirement. Try to have these things closure. Also try to have amplification on the go, which is buffering on the go, so that there is lesser distortion or no distortion. And it also becomes very, very critical for timing critical circuits. Now, in the signal integrity only, another part of signal integrity is crosstalk. Crosstalk means somebody is talking, may say, I'm giving this presentation today, but two of you start to talk with each other. You are not focusing on what I'm trying to give you, and that disturbance might disturb me or the others who are trying to listen, right? A lot of time this happens in the classroom. So that crosstalk happens in our circuits as well. Say we have a stable signal, but then there is a high frequency switching signal. It will always try to pull the signal towards it. Why? Because between the two lines, a capacitor is getting formed. Because whenever there is conductors and there is a non-conductor in between, a capacitor gets formed, right? So this is that capacitance. And this can impact our nodes. A lot of writing is here. You can read it. I will not read word by word. I'll just explain the things to you. So crosstalk for sure is distorting our signal. It is making it behave the way we don't want it to. How can we take care of this? Again, we have to have our widths correct, our metals selected accordingly, and shielding. Remember, we were talking about it in the analog time. Shielding, as the name itself suggests, you are protecting it from something. Bulletproof, as we talk about, right? So there are a variety of shielding, coaxial, sidewall, depending on the requirement that particular signal has and depending on the metals you have with you, you will decide the kind of shielding you want to put and put it accordingly. At the same time, don't overdo it, because the more shielding you put, again, you are creating more capacitors around it. It can slow down your signal also, in case if your signal which you are trying to protect is a high frequency signal. So you are supposed to aware of these issues so that you can take a good decision, informed decision. And sometimes as layout designer, because you are aware of all these things. You are more closer to the understanding of fabrication process and the deformities or defects which can come there. You will also be able to educate the circuit designer about same. So say the buffering, buffer sizing, all these things. Don't just think that it's only the designer who can decide all this. If you are seeing issues somewhere, you not bring them closer. Talk to the designer beforehand and decide together that we cannot bring these 2 points closer, but we will have to have buffer in the later phase. He or she can go and check that how many buffers might be needed, and accordingly you can have plan for them in the beginning itself in your layout. Okay, with that, let's move from here. Congestion, as the name says, right? We are in Bangalore. Hopefully whoever is here from Bangalore, you all know the traffic we see in Bangalore. Why so much traffic is there in Bangalore compared to all other cities? Roads are not that wide and there are too many cars. Everyone has a car, and so then the same thing, what is happening in the traffic, the same thing is happening here. We have lesser resource, like the area is less, but too many lines have to go through. What will happen? Congestion will happen. Now you cannot go straight to the shortest path, you'll have to take a longer route. Same thing will happen here as well. Detouring will happen, longer routing. Longer routing means there'll be timing violation. Longer routing means there'll be delays. There can be the drop of power. There can be routing failures as well, because there is the very long routing and or many jumpers. So the effect of other fabrication failures can also come there. Okay. Now, that is why if we have to take care of congestion, it's very important we think about that from beginning itself. We don't work as in a reactive way in layout design. We have to work in a proactive way. As the technology is shrinking, we are going to lower nodes. More and more transistors are coming in the same area, which means more and more routing will also come. So it's very important at the time of floor plan itself, we think of it and do our planning accordingly. Okay, like you have to go to office every day, try to find a house or your PG or your place to stay closer to it. You have to go to the malls or restaurants someday, so don't go and stay closer to them unless you really want to go there every day. So do that kind of planning, and then you will be able to take care of this congestion problem also. Okay, whatever we are doing, what is the final destination of it? A silicon has to be created. And that process, when we, like in the software industry, we say we are releasing a software, we call it tape out. Because in the long back, in the older days, the layout design used to happen as really like drawing the tapes or films on a given board, and that tape was later given to the fab. So that's why the name is still continuing, tape out process. We did wonderful layout, and now we are like very happy, and we are thinking it will go and make a wonderful, very nice silicon. But to make sure that that really happens, there are some gatekeepers between your layout to the final tape out. And that is what is listed here. As soon as designers are also checking that your layout, they will do their simulations and make sure things are matching. From the layout point of view, there are a few things we should check, like DRC, right? Design rule check. Anything and everything I draw will not go and work or is drawable or fabricatable on silicon. There are machines, right, which are creating these lithos. They will not be able to draw any kind of geometry. There are specified rules given, which is called PDK also. We'll talk about that also in a later time. So you have to adhere to those design. You have done a wonderful layout, but it is not passing DRC. It will not go for tape out. So it's very important that the layout designer understands what are the DRC rules and adheres to them, goes clean, then only your data will go for tape out. Layout versus schematic. Designer has decided something, you are adhering to it. We were talking about this multiplier and finger in the analog part, right? That the designer has said 6 and I can now draw it as 2 cross 6, 2 cross 3 or 3 cross 2. Any which way I want, I can do that. In some cases, it will be okay, and hence my LVS will go past. But cases like if it was a current mirror, it is very important that my source capacitance and drain capacitance are as the designer has expected it to be. Both should match. So multiplier only can work. Fingers will not work. So if in schematic it was drawn as multiplier, but I have drawn it like finger, even though the total width is still 6 micron, in LVS, I will get caught and it will show a failure and I will know, oh, design wanted it in certain way. I have not followed it and I will go correct it, right? So LVS is another gatekeeper. And then design for manufacturability. DRC can tell you what is the smallest manufacturable drawing which can be done. But a lot of time these drawings don't work. I'll just go to the next slide to quickly show you some of the real time failure figures of DFM related issues. So like here, as we see, there are multiple thin lines, right? A lot of routing, a big bus is going. When multiple such lines are coming and the machine is putting those lines one after another, there are chances of them getting shorted to each other, right? Because they'll come so close to each other. So that is something we have to be careful about. Similarly, when there are vias, like connections coming between one metal to another, that stress which came, that can make some short or opens. And sometimes those puncture for the via will not happen properly. Hence, we always say in DFM point of view, in place of one contact, give two, right? So DFM is something which is, even though your DRC is passed, we will also see that all the things you have drawn is manufacturable also or not. And then comes tape out document. Every company, every organization will have some rules defined that you are adhering to them or not. Because again, there are some rules which are generic, common, and there will be some rules which will be very specific. So those documentation also need to be taken care, and then only you can go for tape out. So these verification constraints one need to understand very well. Otherwise, whatever time you put in drawing a wonderful layout, it will never see the daylight. And a few words which I was using here, make a note of them. It will help you later. PDK. PDK stands for, it is the physical design kit. So it'll have all these rules which we are seeing here, right? For DRC, for LBS, there are different foundries, right? You all must have heard names like TSMC, UMC, YMC, all these companies. They all will have their own rules based on the devices, the tools they are using for fabrication. So all that rules together makes this kit. EDA tools, when you are drawing schematic or you are drawing layout, you are doing it on some of the tools, right? These electronic design automation tools are the EDA tools. Companies like Cadence, Synopsys, they have their tools in industry. There are also verification tools for LVS and DRC, which also comes from different companies, and that is what also one need to be aware of. You need to see, understand those tools to be able to use them efficiently. And the checks, what we were talking about here, right? Manual checks are always prone to manual error. So how we can automate it, that all we should be aware of. Okay, now skills to build as a layout designer. I think we have time in hand.
Shweta, it's 9 o'clock.
Mm-hmm.
Can we wrap it up in 10 minutes?
Sure, of course. So skills to be built as a layout designer. There are some foundation skill like must have, which are never think that I'm a layout designer, I'm not a circuit designer, I don't need to understand CMOS fundamentals. No, That's not true. You have to understand CMOS fundamentals, then only you'll be able to take good, correct decisions. Digital analog basics you need to understand, and the device physics you have to understand, then only you'll be able to take in account the parasitic, the actual physics of the fabrication stuff. On top of that, if you also understand different types of layout, what we talked about today, matching techniques, verification techniques, and you have good exposure of tools, that is very good for you. That's the added advantage you have. And then advanced thinking. When we are saying advanced thinking, things which can make you stand out, like you are aware of the issues we were talking about, the RC impact, signal integrity, how to debug. A lot of time it happens, you will do the layout, you will be like all good, but as you will start verification, some errors will come and you'll be stuck there. We had one incident where we decided that maybe in 3 days we'll finish this layout, but we got stuck with the verification, and it took us extra 5 days, which we have not even accounted for. And you should always be able to take an informed decision between power, performance, and area, right? Because there'll always be times coming where you will have to pick one of them. So you should have those understandings. And hence, I say that a good layout designer is not somebody who just follows the rule. A good layout designer is somebody who understands why those rules are there. Because when you'll understand the why, you will take good decisions. Few things to show now the gist, what I learned in industry. Because whatever we see is one thing. There are, of course, things we learn on the job. Layout is an iterative process. Never think that, oh, I made it and it is done. It will go for simulation, some changes can come. You are doing the layout, meanwhile, they are checking, the circuit designers are checking these schematics, they found some other thing, some change can come. So always be ready for change even till the last minute. Small decisions have large impact. The basic cells, the bit cells, small changes, small things, it can have a bigger impact. Some decisions you are taking at the time of floor plan can save you for congestion at the later time. So every decisions had to be judged well. And the debugging, as I was talking just a few minutes back, debugging can take more time. So always account for that. And collaboration is very, very critical. You can never be a good layout designer by just being in your zone and doing the layout all on your own alone. You always have to collaborate well with the designers, because when you will understand the circuit, you will do a better layout. You always have to understand the tools, so have a good relation with your CAD people, and you always have to understand different types of layout, right? So don't be just in your zone, collaborate. So a good layout engineer don't just draw, they anticipate the problems before they appear. And with that, we are at the last slide, that great chips are not just designed, they are carefully laid out. Thank you all for listening to me for so long, and we can take any question answers. I mean, any questions if you guys have for me, I'll be happy to take that. I hope I wrapped up quickly, soon enough. Am I audible? No questions?
Yeah, am I audible?
Yes, yes, you are.
This is Arun. Thank you for this wonderful talk and giving us the insight exactly with respect to the industry insights and the experience that you have shared. I have just a question. I'm from academia, and when we talk about layout designing, and when we talk about the industry in the VLSI domain, semiconductor domain, just wanted to know that how you see that the applications of AI coming into layout design and all.
I was expecting somebody to ask about AI for sure. And AI is something we, in all the field, we are trying to take use of it, right? As we were discussing, there are designs, there are types of layout which are very repetitive, in such scenarios where there is repetition, we can use AI in a wonderful way. We can give those test cases and we can create utilities with the help of AI where we can take care of those repeated work. Still, there will be places where complete thing going to AI will not be possible, at least for coming few years, because there that manual understanding, like our analog layouts, right? You have to take the decision based on the scenarios which are in hand. So there maybe it will take time, but in many areas, of course, AI, even the tool vendors are looking into that direction. Most of the bigger tool vendors, the EDA tool vendors, are coming up with AI empowered or AI powered versions of their tools so that we can do the layout in faster way.
Yeah, thank you.
Thank you.
Also, there are a few questions in the chat.
Okay. Would you like to help me with those questions or?
Oh, no. I'm so sorry, sir. I just rejoined. My messages got wiped.
Okay, I'm seeing quite a few of them. Okay, let me check. So I think there is a, how is analog layout different from physical design? Okay, when we say physical design or PD, it is mostly referred to a RTL based design. There will be logic written, logic gates will be there. Using those gates repetitively, we are creating the circuit. So that is done completely on the tool, whereas layout design, custom layout design is more manual compared to the physical design. So that is the main difference you will see. It is not automated, it is not done through tool. When we have an analog layout, why do we need PD? Okay, because there will be some places where it is very logic heavy, right? We can draw it with hand. Long back we used to do that, but it will take a lot of time. Also, with the help of PD, you can do it faster. You can close the timings easily because you will do placement, etc. As per that, analog layouts work beautifully for specific scenarios like critical analog blocks. PD is only for our logic gates. Okay, any other question I'm missing? How can, as a student, move from theory subject to actual understanding layout? Are there any tools or small projects you recommend starting with? If in your college you have access to the EDA tools, I would suggest start using that, practice more on that, start from smaller circuits like some of the basic gates and then move to at least a op-amp or something. With that, you will understand quite a bit of concepts and you will also be clear or more confident with the use of EDA tool. Okay, I think I tried to cover whatever I was able to read.
There is one more question, ma'am. Why are there less openings from analog layout freshers?
Well, I won't say that there are less opening for analog layout. There are different companies making different kind of chip, right? So the requirements of the product and requirement of the individuals to do that work comes hand in hand. There are many places where analog layout designers are looked for. So it's there. Maybe search a little more, you'll find such openings as well. Okay, I see one. Is Cadence enough for layout? Cadence Virtuoso tool is the widely used tool for layout design, but there are tools from Synopsys as well, and there are some startups or companies which also make tools on which we can do the layout design. So that is not the only one, but that is the most used one in the industry.
Hello.
Yes.
Yeah, can I ask it? Do you have time? Can I ask?
Sure, I think we can.
Yeah.
Maybe a minute.
Sure,
Minute.
please.
more. Yeah, sure.
My name is Girish, and thanks for a nice presentation. My experience with chip designing has been mainly in universities and not in companies. With that, I have a question. In standard cell layout, the routing is done with two layers,
Mhm.
right? And in one of the technologies, I have seen the routing being done with metal one and poly.
Mhm.
Uh, for me, it was a bit unusual because I didn't expect a poly to be used for in a standard cell layout.
Mhm.
My question is it something normal? And if it is yes, then why poly?
Okay, so it all depends on how many routing resources you have. In some technology, you'll have 7 to 8 metals. In some technologies, you'll have 13, 17 metals also. If you have many metals, you will want to use them at next level, and hence on the standard cell level, we try to use less metals. Now, if your routing resources are less, then sometimes poly also gets used for routing. It's not the best practice, but at the same time, it's also not something which is not advisable at all. We can use it for smaller distance. For example, you have multiple transistor, and now you just have to create a jumper. As you want to stay within 1 or 2 metal only, then how you can have another jumper if you don't have more resources? So for those smaller length, we do use poly, and we keep a tab on it, say only not more than 5 micron, not more than 3 micron. Go for smaller distance routing. Very long routing, we try not to do with poly, but it is normal in industry.
Yeah, the technology had only 5 layers of metals. I think that's the reason they used. Yeah, I have
Can I
one
add
more
a,
question.
can I add a comment
When,
here? Yeah.
Yeah.
Yeah,
Hello?
Girish, no, I Lakshman here.
Yes,
I
please.
mean, it was, yeah, maybe
Yeah,
I know,
yeah.
because Girish, just to be related compared to
Lakshman sir, your voice is unclear.
make that. Not good.
No, sir.
Can't hear you, Lakshman.
We are getting a break from your voice.
Okay.
Uh, so still you are not audible.
Just continue.
In the meanwhile, Sweta, can we go for one more question? We got it in the chat box.
Yeah.
from-
Usually, when the extraction is done, I see only R and C are considered, and why L is not considered usually.
Okay, because it actually depends. If you are working in RF layout, RF based layout, then L is also considered. But in many other places, the effect of L will not be so much. So if it is digital layout, if it is normal analog layout, that effect we exclude. But for RF layout, we will consider the effect of L as well. So it does get into account.
Okay, fine. Thank you.
Welcome.
Okay, can you hear me now? Sorry, is it better?
Yeah, yes.
Yes, you can hear.
Okay. Yeah, really sorry for that. I was just outdoor. Yes, Sweta, it was a wonderful presentation. Thanks a lot, and for covering the entire spectrum pretty much right on the layout and giving your perspectives and views and insights from your experience. It's wonderful. Very quickly, Girish, if I can touch upon those two questions in the interest of wider audience, just to expand on them. Poly, as you see, it has its purpose is primarily for a gate, formation of gate, right? It has a slightly higher resistance and a relatively higher capacitance to the active also. So it can be, I mean, as long as you know what are its electrical characteristics looking at the PDK, as long as you can manage with those, I mean, understand every layer has a different electrical characteristics, resistivity, their fringe capacitances and lateral and longitudinal capacitances and all of that. As long as you understand that and you can live with that for a given purpose, you can use any resource, no problem. That's one. Second, coming to the inductor, it's primarily dependent on frequency. Even in RF, sometimes low frequency RF, it really depends actually. Many times it's a thumb rule. As you know, for a length of wires that we are drawing, right? The inductors that can reasonable inductance values that we will get are extremely too small values, and they don't give any perceptible differences in the frequency of operation that we deal with. Even in digital, when you go to tens of gigahertz, higher frequency inductance will matter actually.
Okay, thank you.
Very high speed digital, it's mainly the speed, the frequency does matter, not the RF versus digital versus analog alone. If it is a low frequency RF and a high frequency digital, still these will make a lot of difference.
Okay.
Thank you.
Thank you so for your comments, and thank you, Sweta, for your nice presentation. And today we have a participants consistency till 9-10 around 40 plus. That's a great turnout ratio. And from the IEEE CEDA Bangalore chapter, a small token of appreciation from our end as a model of virtual meetup. Thank you again for enlightening and guiding us throughout the event. And team, if you have any more questions, we will share the feedback form to you. Please write down your questions. I will forward it to Sweta. And once I get the answer, I will share it back to you. And I'm so sorry for the last time for the episode 2. We have few technical issues while sharing the certificates and other aspects. But this time we'll try to make it complete by this within 1 week. And thank you again for joining. See you soon in the next episode. Signing off. Bye.
Thank you, everyone.